Well, thank you everyone for joining. It's in the afternoon and hope everyone's lunches was great. Today's conversation is going to be around the evolutions of artificial intelligence, machine learning, and deep learning. It's part of my passion. I really enjoy this to speak in this presentation I'm going to present to you, and it'll make you think outside of the box as well as you go to these conferences. And I go to Black Hat and DEF CON, you hear these words, right? AI, machine learning, deep learning, and what does it actually mean? And today I'll have images for you and explanations for you so that you can be a little bit smarter when you have those type of conversations. At the end of today's call, I'm going to also share you a website that you can see if there's any jobs opening for my company at Deep Instinct. I always like to introduce that so that if you're looking for a job, we do have openings. We are a mid-sized startup and we're growing exponentially this year. One moment. Let me just all right, a little bit about myself. I'm going to pause here and talk a little bit about myself, my credentials, and where I came from. So I'm a cyber security solutions engineer here at Deep Instinct, and I'll tell you a little bit about the company, but I really want to just focus around the conversation and my company. But I want to take a second to pause. If you see this QR code, I believe anytime I go to a conference, I try to meet as many new people as I can. So what you can do with your phone, and I'll give you a few seconds, is just open up your camera app and point it at this QR code. It will point you right, if you have the LinkedIn app, it will point you right to my LinkedIn page where you just simply hit connect and say hi or something. I'd really appreciate that so that we had this deep conversations with each other. And if we need to continue it in the future or anything about cybersecurity, I can assist. My background, I am a mentor for Cyber Patriot. I do that, and was one of my passions to help high school students, learn about cybersecurity. I volunteer and help this team get into cybersecurity competitions and then win scholarships. So local to Northern Virginia, this is something that I do on the side, and that's how I started my cybersecurity career. Well, call it adventure, say. I help students. I learned, the Security Plus techniques and CISSP, and I train these students how to do some basic level pen testing or defending of their machine boxes, and this is through Cyber Patriot. And I've grown beyond that, got a job into cybersecurity. I was a firewall, cyber solutions engineer at Checkpoint before joining here at Deep Instinct. Moving from then, about 4 years ago, I joined Deep Instinct, and now I help local departments, state and local, hotel chains, university and colleges, and consult them about cybersecurity and the threat landscape and how we adapt to this changing culture of, I have this product, how do they combine, what is the best of breed technology? And that's something that I enjoy doing every day. And I do it at nighttime too. I consult the Asia teams over in Japan and Taiwan, and that's quite fun, the translations I have to do. But that's my past. Graduated from Virginia Tech. I'm very proud about my alma mater, and thank you. So deep learning. There's content available at these links actually are, you can click it within the PowerPoint, but you can't click it if you're looking at the PowerPoint. I'll share these slides with the team, and if you actually message me on LinkedIn, I'll send you these links personally. And these are just some of the deep learning. There's a deep learning dummy for dummies here on the right hand side. I can give you a free copy so that you can learn the basic level of deep learning and have a book for you to read in the next couple of days. And then there's also ebooks and videos that I can share with you. But let's start. What is deep learning, right? You may have heard it, you may haven't. You're actually using it every day, or it's being used against you every day. And I'll tell you how. But first, before I tell you about deep learning, which is a subset, if you look at the timeline from 1950 to 2010, it's an evolution. It's the way technology has evolved. Artificial intelligence started in the 1950s, about the time when I would say computer science came about, the need for a computer to do what a human can do, calculations, a human teaching a software to do things that to automate things. And that came out of artificial intelligence, not the Matrix. Of course, the Matrix actually before the Matrix, right? And then became machine learning. Machine learning was the thought of, all right, now I can teach a computer what to do. I can teach a robot to do certain things, like you go into a factory and a robot can pick up, certain objects. But machine learning takes it a little bit a step ahead. In 1980, machine learning, the algorithms became a little bit smarter to say, all right, well, let's correct for error, right? You pick up a bottle, but it misses. So what about next time? Can it fix it so they can correct for error automatically without the human going in and doing it for them? And that a good example of machine learning was about late 1980s. There was this IBM came out with this Eternal Blue, I believe, or it was Project Blue, where it was a chess player, a machine. It's a computer chess player that was taught how to beat the best chess player in the world using algorithms, using a learned mathematical algorithm to defeat the best player quickly. And that was machine learning, right? It didn't come out of saying, all right, I taught it to do something and it did it. It was more of, let's learn how artificial intelligence, these algorithms, learn how human behavior works. Oh, I have a question here. And I believe we're going to be, I'll answer questions at the end. Actually, you know what? Give me one moment. Let me see if I can view the questions while I talk.
I've got it. He said deep blue.
Deep blue. Okay.
Yep.
Deep blue. Yeah. Thank you so much. All right. Thank you for correcting me. Sometimes I forget these things.
Yeah, and I have the chat window up. So if anybody types in there, I'm on mute, but I'll try to get off mute quick for you.
Awesome. Yeah. Okay. Yeah. And keep asking me questions and add anything to my conversation, because it's kind of a small group here. So I appreciate your time. And then deep learning. Deep learning evolved out of machine learning, where instead of you teaching the robot what to do, you actually give it examples, right? In terms of deep learning, I'll give you some examples today. Say, for example, you give it 100 ways that a robot, instead of telling the robot what to do, you say, robots are supposed to do this. And the robot is then able to learn that because you show it what to do. But if you show it 100 times what to do, then you don't have to teach it anything. You don't have to create these algorithms. It actually teaches itself. And I'll go into a little bit more detail on that. And that came out around 2010, around the age of graphic processor units and the need for video game systems to learn human behavior. And I'll show you some logos here that you might be interested to see. All right, so let's go into a little bit more detail about the three categories. Artificial intelligence, right? These are some of the topics that came out in the 1950s. The basic example of any technique that enables a computer to mimic human behavior. So that's robotics and language processing and logic and planning. Evolved from that is machine learning, where you now have decision trees, Bayesian models. It's a technique for computers to learn without being explicitly programmed to do so, right? So the nearest neighbor, learning about trial and error with reinforcement learning. There's a lot of terminology here, and if you ever take computer science and learn math, and there's a math portion to it, you'll learn some of these techniques that are used in machine learning. Evolved from that is the artificial neural networks, the deep learning. Now it uses all the concepts from artificial intelligence and machine learning and adds on to that, where now you're looking at neural networks, you're now perceiving and predicting the future almost. And it's multi-layered. It's, instead of it being linear, you have different layers to it. And I'll show you through pictures what I mean by that. So let's go backwards into 1950s, 1980s, classical machine learning. And I'll tell you then how this applies to cybersecurity. I know it's a little, you see cats and dogs and you're not sure how this can apply to cybersecurity, but I'll tell you how these are all evolving into how we're protecting malware today. So the general machine learning approach is you label a cat. A human goes and labels a dog based on the human, right? The human goes and says, this cat is labeled a cat. This is a dog because we know it's a dog. You train them, you train the system, and you create a model. The model will say, all right, now whenever you see this picture, it's a dog. Whenever you see this cat, it's a cat. And it takes features. And what we have to do is there's two features that we take from these pictures, from a human perspective, to apply mathematical algorithms to it. So what you do is look at supervised learning versus unsupervised learning. The basic concept, if you hear those two terms, just think of input data as labeled versus input data as unlabeled. In supervised learning, you say, this is the size of this is the length of the ear for cat. So that's a label. Versus unsupervised learning is you just see a picture of the ears of a cat and you say that's a cat, and you haven't labeled it yet, so you haven't created the attributes. And so there's two different types, and it requires both supervised and unsupervised learning in order to build these algorithms. Let's take a look at that, right? So with machine learning, you take raw data, you take a picture of a dog, and then you do manual feature extraction. You say, this dog, because it has a long snout, that's what makes it a dog. The eyes are a certain size. The ears flop down. That's what makes it a dog. So you extract, in that case, 3 features. You create handcrafted features. You create an algorithm, and then now you have a machine learning to say, anytime these 3 things combine equals a dog. And this is just a little bit deeper example of that, where in centimeters, and you're actually creating measurements against it. What about machine learning? How does that apply to misleading features, right? So when you teach a dog, when you teach an algorithm to say, this is what a dog looks like, but this is what a cat looks like, in your eyes, you know what the difference of a dog and a cat is. But if you only taught the machine learning algorithm, and right now I'm going to debunk machine learning, if you only taught it that the ears are long, then what about if a cat's ears are long? Or the face of a dog is round and the cat's face is also round? What is this called in cybersecurity when you teach something a feature and it catches it incorrectly? This is called false positive. Now you have a false positive that this cat is actually a dog, or this cat could be labeled a dog. What about noise? A lot of times cyber criminals, what they'll do is they'll create, and I'm trying to create an analogy here, instead of being a normal original picture, these are original pictures, they add features to it. They create noise. Instead of it being a PDF, they change the malware into a Word document. And now it's changed its structure and it's hiding itself. They create noise. And how do you teach a machine learning if it only looked at the ears being long, but then the ears are now missing, and it didn't account for the face, right? So this is just a picture analogy of how cyber criminals are creating mutations of malware. Okay. For example here, this is an example of a malicious font file. On the left here, this is malicious malware. You can see on the bottom here, this is where the code ends, the malicious content ends. And if you look at the malicious mutation, only changing it by 1 character now bypasses signature-based attacks, right? If it's a signature, now the hash has changed, or the SHA-256 has changed. Or if you taught the machine learning to only look at this row and it changes rows, then in this binary of malware, this malicious font file, and it changed the locations, it's going to say, all right, well, this is not malware anymore because it's not in the same location, but you only taught it that certain sequence, that location. That's just an example of signature-based, or the way machine learning would think about it. So yeah, 1 byte offsets completely changes the verdict. So why not let a model decide on features? And that's now we're moving into the generations of 2010 deep learning. So now deep learning is very similar to the way the brain works, training the brain. And when you teach a child, the difference between a dog and a cat, you don't teach it based on features. You teach it based on examples, and a lot of examples. Every time you walk your child down the street and you see a dog, you point at that dog and you say, that's a dog. Next time you go to a dog park and you say, those are all dogs, your child is then able to quickly learn through examples that that's going to be a dog. And then you teach it for the cat, and now it's able to differentiate the difference between a dog and a cat. And even the fact that you can look at different types of dogs. This is a Chihuahua. This is a small dog versus a big dog. This is a dog that you should stay away from, right? So the detection becomes instinctual. And that's, now we're applying that to cybersecurity, where we're creating artificial brain. This is artificial brain by deep learning, is very similar to the way the human brain works. So you have in the human brain stoma and dendrites and axons and terminals and the synapses that teach, the behavior of, something hurts, or you see a dog and a cat, it changes different parts of your brain, smells and everything. Well, the neural network is very similar. You create a lot of inputs, you put weights to it saying, is this right or this wrong? And then you create a output to say, based on what I've learned before and all the inputs, the millions of inputs that I've received, creates an output of, this is what it is. This is what I perceive it is. And it requires all the supervised, unsupervised layers in the neural network. And I'll go into a little bit more details on these 4 topics. So deep learning is not a marketing term. It's actually something that came out of first publications in the 1960s and 2000s. If you actually look up deep learning, an example is COVID-19. They're using deep learning to correlate early detections of the lungs, x-rays of lungs, in pictures of lungs, and the computer is able to say with a high, I think 90+% efficacy, that this lung is COVID versus a flu or influenza, based on how the virus is impacting this person's lungs. And this is using deep learning. So it's impacting the medical industry. It's also now applied to cybersecurity. So there's theoretical advances, and in the 1990s, a lot of labeled data sets. It requires a lot of data, right? It's not something that you could say, based on 5 samples, I could make a correlation. It's more like 5,000 or 5 million, and it's done by data scientists. So it requires a lot of GPU computing. Around the time of, when graphics processors became very, very powerful, I would say NVIDIA and AMD and all those companies have created the most powerful part of your computer is your GPU, if you have a nice one. And that GPU can crunch a lot of data. And we're utilizing the GPU to crunch all these malware samples, and the scientists are crunching all the data from their research studies to create algorithms, instead of having to create algorithms themselves. And in 2008, open source frameworks. You create these frameworks. I think there's 5 main frameworks for deep learning, and in my company, I'm proud to say we created our own framework for cybersecurity. All right, so let's review a little bit. Okay, so let's review a little bit about deep learning versus machine learning. On the top is machine learning. You have the raw data. You have manual feature engineering, right? So you have a person to say, this is what malware is, this is what malware isn't, because of these 10 things. You create an algorithm. It could be mathematical, it could be theoretical, and then you create a machine learning algorithm, right? But deep learning is different. Instead of having a human come in and a human be in the picture, it just takes the raw data. It takes hundreds of pictures of those cats and dogs. You tell it what the difference between a dog and a cat is, and then it's able to learn based on examples. Or malware, you give it millions of malware samples, looked at the binaries, and then is able to then create this correlation to say, based on the binaries, based on the core of a program of a malware, and we've trained it, there's these millions of ways that these mutations that could happen, that we can actually identify it as malware, and quickly too. So it's much quicker to use deep learning. And here's a little bit more difference between machine learning and deep learning. Because it requires that human interaction, a human can only tell what they see, right? They only can tell what the picture of the dog and a cat looks like, and the features of it. And it only extracts certain features, and that is really only utilizing 2% of the data. If you have a malware sample, for example, that is say, for example, 10 megabytes, is a human able to analyze every single bit of the code in that 10 megabytes effectively? And we've tested it and said no, because humans have, time. It takes too much time, or they have to work on different projects, and they had to prioritize certain parts of the malware sample. But with deep learning at the bottom here, you feed it 100% of the data, and it's able to create an autonomous, intuitive, automated, nonlinear model of correlation, right? So now it's not from A to B or A to C. There's actually a three-dimensional way that we look at malware and malware code. And also machine learning limited to certain file types. If you look at portable executables, or only look at documents, and you only categorize, what the latest threats are for PDF files, for example, it's going to be limited. Your machine learning is going to be limited to the file types that you can train, the human has to train. Versus with deep learning, you give it 1 million font files, benign and malicious, and it's able to tell the difference between what's delta, right? What is the mutated one? What is the one that includes a ransomware inside of it? And this is just reviewing the debunking machine learning, in that, not debunking, machine learning is great. It's good with its uses, but again, it's just the limited human knowledge and expertise, right? Human only goes through and looks at part of the 10 megabyte file versus the full raw data. And then mutations. If you only teach it one way to look at malware, or 10 ways to look at malware, what about the 11th or the 20th or the 100th mutation of it? And here's a nice picture here to summarize what I was talking about. This is the way the human looks at a file, right? You write code line by line. You highlight. When I was an engineer, a reverse engineer, I would highlight things that would make the anomalies look malicious. The ones that I think that this is calling out to a command and control server or something. But deep learning has made it so much more simple. I just feed a bunch of these files into my model set, and it's then able to say, based on 100 samples, this is 90% ransomware. And it's able to categorize and tell me what malware is and isn't. So in that case, I'm feeding it 100% of the data. It's autonomous. It's automating my data sets and categorizing it, and I'm able to train it on unlimited training samples. And apply the inputs from many different types of devices. So it's operating system agnostic. So you can actually learn malware in any type of operating system, including Android phones, right? We have a lot of malicious apps that we're looking at, and we have a lot of apps in our Google Play Store, even Chromebooks, that we're looking at, and we're feeding this neural network of all the malicious things, and then taking out protections and prevention capabilities against it. More statistics. This here on the top is machine learning. The accuracy with unknown malware. So this is actually with known malware, machine learning signature-based can protect. Unknown malware, where it's mutated and it's new. And actually, if I have some time today, I'll show you an example of some unknown malware, and I'll execute it on a computer to show you that with deep learning, you can actually prevent an unknown malware attack, a mutated one. So with that, you could see with accuracy is 99% and very low false positives with deep learning. So here's some real world applications of deep learning. You might see here some familiar, I know you know these logos, but let me just show you one facial recognition by Facebook. 5 or 10 years ago, Facebook wasn't really able to do really good. Their image recognition was very subpar. It was you uploaded a picture, and based on location or based on your friends list, they would able to categorize and say that could be you. But now image recognition has gotten so much advanced. It has advanced so much that now with even a picture, I have a hat on, and if I upload my picture right now to Facebook, it would actually be able to tell me that this is me and not my cousin or not my brother. Uh, and even your friends, right? If you have a picture of a group of 10 people and they only see like one part of your face, the image recognition using deep learning is able to say, all right, well, based on the percentage, we're gonna say this, we're gonna tag this friend in your picture. And that's advanced so much now that deep learning is involved. It's trained on your pictures. It trains on your and now Facebook has this neural network of all your pictures and the pictures around the world, and it can correlate without using the small features like geolocation and that being your friend. Is able to correlate based on part of your face or even bottom of your nose. And it's doing that in image recognition and in many ways in Netflix, right? Able to do recommendation systems and learn your behaviors. To highlight deep learning, deep cybersecurity, Deep Instinct is the first and only, and this is my company, and I want to represent the data sciences engineers who created this cybersecurity platform, where we're the first and only cybersecurity to provide end-to-end protection with deep learning, utilizing deep learning neural networks to prevent cyber attacks. And that's quite a feat. So it's used in many ways. 90% in computer vision, speech recognition. You go through Google Translate and it's able to actually caption your voice and caption the translation of what you're trying to catch utilizing deep learning. And if you actually look at jobs, you go to Facebook jobs or Google jobs or even Tesla. We're not affiliated with them, but I just want to say, for example, like Tesla, and you look up deep learning, you'll see that they require some of those that knowledge of deep learning in order to produce their algorithms for looking at stop signs and image recognition. It's not so much used in cybersecurity yet. So we're actually in a new frontier. Only 2% of companies are utilizing deep learning today. And so it's an open market for cybersecurity. And there's a lot of traditional machine learning, right? Feature extraction, but this pure deep learning is very new, and proud to be part of the frontier. So the benefits of deep learning to cybersecurity, where this is BSides. So let's talk a little bit cyber, right? Prediction of unknown threats, zero-time detection and prevention, and I'll have some time today. It looks like we have about 15 minutes left. I'm actually going to show you an example of a zero-time detection and prevention of unknown malware, or zero-time malware. Sorry, not unknown. It's going to be malware that is found within the last 12 hours. Yeah, and it's cross-device, multi-operation system. So as you saw in my maybe 3-4 slides ago, there was some. It's operating system agnostic. So we've trained this brain that now sits on your computer, your desktop or laptop, utilizing deep learning to protect against cyber attacks. And it doesn't require any internet connectivity. So you can have protections on your computer without having to have connectivity to a cloud server. It's connectionless, because your brain doesn't actually, you don't get information from an external source. It's everything in here. It's in your noggin, right? And that's deep instinct in deep learning. It's everything is now on the computer. It's like an analyst that checks everything for you as it gets written to disk. And here, this is a good one. And then this is going to be my last slide before I show you some examples. Let's show you the way that Deep Instinct has applied deep learning from training to prediction to response. So it starts off with malware, third-party sources, darknet, homemade malware, mutated malware, millions of malware in malware file types, executables, PowerPoints, XLSs. And as you saw in my previous slide, where a human has to go in and highlight all the malicious parts of a Word document and then create a signature for it, we're just giving them files. We just give this neural network all the files, and it's able to crunch it and say, based on these million files, a million, 10,000 of them are malicious. And what of the 10,000 malicious ones are makes it malicious? And then it creates this whole pattern of malware samples and able to predict. All right, well, let's give it a separate sample set, of another 100,000 malware. Do we see some similarities between the first sample set and the second sample set, and then creating correlation against that and creating another algorithm or another pattern, a deep learning brain, right? And you just teach it this way. Hopefully that's clear. I'll pause a little bit for you guys to kind of read through this. So it requires a lot of these data sampling, supervised training, and creating noise, mutating malware, tweaking it a little bit, maybe adding a different line, and then going with the protections. And it's through this deep neural network, we train it through NVIDIA GPUs. So NVIDIA is one of our partners that we use their business GPUs, not those 1080 Ti's or the 2080 Ti Super, 2080 Super now. I think it's the best one for consumer base. I like the game. I like the game a lot, but so 2080, those are consumer based, but then they have these business grade GPUs that actually did sit in the NVIDIA data centers that we partner up and we train our brain and our neural network with their GPUs. And it only can be done on GPUs because of how much data that's being added to it. So once it's trained, it takes about 24 hours to train. It's then we create these petabytes of data into one single agent. And this is where deep fencing is. We are an endpoint security company. We provide endpoint security on devices, laptops, desktops, mobile devices, and we look at any file, any device, any OS. And it's a lightweight agent that runs on any very low CPU and only requires 2 updates a year. So this is Deep Instinct, that's our market. It's the threat prevention, threat detection and response, or predict and respond. And requires only 2 updates a year. And that's actually pretty powerful, because if you think of it, how many times do you have to teach your brain what the difference between a dog and a cat is? You don't have to teach it anymore because you already learned it 10 years ago or 20 or 30 years ago. Same thing for the brain. You've already taught it what malware binary looks like, and then what malware binaries could be mutated to look like in the future. Then you don't really need to have signatures. So it doesn't require signatures. It just requires a new brain. So we update the brain 2 times a year. So with that, is there any questions? Before I start, I'll do a little demo so that you can see this in action. But are there any questions so far? Have I intrigued you guys based on the topic today?
Yep. So we do have something that has come in to us.
Mm-hmm.
Let me read it. We have seen stories of bias in learned algorithms, i.e. mortgage decisions maintained racial bias from the people that were watched, or computers seen so many pictures that they assume coders are men and women who are in the kitchen. Are you seeing that bias in the learning in the cybersecurity implementations, examples and how to fix them, etc.?
Yeah. There's bias. Yeah, bias comes from the human. Yeah, there's a lot of, even in deep learning, I can say that bias is always added by the way you train it, the weights that you put on it. So there are examples. So say, for example, let me show you here. I don't have a picture, but to kind of put it into perspective, if you teach malware too much, if you teach the neural network too many times, and you teach it too many malware samples, what will happen is then you'll get a neural network that only learns it only can find malware. It doesn't know the difference between malware and benign. So what you have to do is you have to create a baseline. And the way to create a baseline is you say, what is clean versus what is malicious? You don't always teach it on one thing, right? To only catch on one thing. And that comes out false positives, because if you only teach, malware and you teach it too many times, then you overteach, you overcompensate the algorithm, and there are 2 things that could happen. One, it won't catch anything. You've taught it so much that it won't be able to say the difference between wrong and right is, or white and black is. Or the second thing is you'll catch things, but it will be false positives because you don't know what's clear and what's actually the gray area. And so you fix it. You fix it by, in part of the training. Actually, if I go back a little bit, part of the training is a balanced data set, right? You want to balance. You want to balance and not create too much noise into the samples, and just enough. And it's also part of Deep Instinct's IP. Our data scientists, they have this they know how to not do too much or too little, and that's the whole brain behind putting it into a client and protection. In more details, Jeff, I can go offline. I have actually had different slides on pure deep learning, and we can go into a little more detail if you like to look at that and examples in the real world without outside of this call. But hopefully that's able to answer. Overfitting right here. Overcompensating, what I mean by that is overfitting. Avoid memorizing the specific files available in the data set, right? You don't want to teach it only one thing and it starts to only look at that one one thing. And that's overfitting is a deep learning terminology. Yeah. And if I go back to one more example, how do you fix it? It's right. For the example with COVID-19 and they're using deep learning, you show a lot of pictures of the COVID-19 lungs and you show a lot of pictures of the influenza lungs, but just enough for both, so that you don't only teach it that COVID-19 lung and everything else is negative and false positive. I just wonder in my head, how many influenza patients are actually being diagnosed as COVID-19. I don't know, but that could be an issue right now. All right. False positives. That's really bad. No false positives. Okay, here, let me show you an example here. I've created a lab for you. Let me go into my VM. I create a sandbox environment, and this is a typical one that I share with prospects and clients and run through POCs. So VirusTotal. VirusTotal is it's a database of uploaded malware and uploaded malware samples. And a consumer-based VirusTotal will allow you to upload any document that you find suspicious into this database to see if any other vendor has detected as malicious. And once it's uploaded, it creates a signature, and other vendors are able to use that. With Deep Instinct, what I like to do is I look at malware that is less than 12 hours old. So if everyone can see my screen, it's June 13th, and 12 hours from now, I'm looking at portable executables, and just to create a nice little, so I'm not looking at false positives, I look at 30 other vendors that find it in less than 45 detected. So let's take a look here. I have the Deep Instinct client installed on my device. It's not using any signatures. And this is a client that sits on the mobile device or a laptop or even server. And it's able to, as I'm downloading each one, prevent each one in real time, right? So it's able to identify this is a PUA. That's through deep static analysis. This brain is able to detect that it's a PUA. And let me show you another example. Download error. Before the file, so every file that's being written to disk, it's intercepted by this brain to say, all right, I'm going to prevent this right now before it could actually, and it goes so quickly that only a temp file is found. Not even the full file is even being able to written to disk. Let me show you another. Sometimes portable executables are easy, right? You can name it a potentially unknown application. What about a PDF that's actually a malicious PDF? So chapter 1 or story. So when you're looking at other samples right here, PDF, there's a Trojan inside of this PDF. Or I'm going to close this PDF failed to error. So this was only it was probably less than a megabyte, and it was already prevented in pre-execution. So this is called pre-execution, where it doesn't sit on the disk, doesn't require sandboxing. It never actually executes. It's intercepted at the, look at here, it's like at the Chrome cache level, right? Before it can even be written to this, it's already been analyzed and prevented. What about another way? A lot of machine learning some engines don't look at RTFs, which is a font file or a file that has certain macros inside. So right here, same, I couldn't find ones that were today because not many malware come in RTF format, so I had to do a couple days, but that's beside the point. Let me just download an RTF file. Failed to download, so quick, right? So, and then I can go into the here with virus total, and I think I clicked on something by accident. I can look at this hash, and these are all the other signature-based protection, and these are some of your consumer-based signature protections are able to count as malicious. And then there's some of the machine learning companies out there that undetected because it isn't one maybe not able to look at process the file type. The file type is RTF and it's not added in the machine learning. It wasn't trained on RTF, or it's undetected because there's no signature and there was no machine learning algorithm that was taught about how PDFs can be manipulated, or RTF in this example. I like to point that out. And Deep Instinct, the actual client, is actually 3 months old. The signature is 3 months old. So 3 months ago was the latest update on the client itself. And Deep Instinct endpoint protection, and we're protecting malware pre-execution. And that's the way it works, online and offline. How about this? Since we have a little bit of time, I'm going to disconnect my internet. So now there's no internet connectivity. And in here, I downloaded the top 25 malware samples, and I'll extract here. So the password, so I downloaded the top 25 from VirusTotal. And as each file is being written to disk, it's actually being deleted, quarantined, removed before it can infect the computer. It doesn't even have time to sit on the disk. And this brain is able to understand. I haven't ran this one before yet, so this is brand new, and this is offline. This is no internet connectivity. 25 out of 25 samples prevented in 0 time. This is with deep learning. This is Deep Instinct. And this is what we've created, the algorithms from AI, machine learning, now deep learning to apply to an endpoint security product. All right, without that, yeah, that's just some of the cool examples here. I hope you guys were intrigued here. I think that's fun. I'm glad all 25 samples were caught. I feel safe, and the user never, in phishing attacks, right? If you get an email with the PDF that's malicious, boom, the engine the brain will then detect and prevent the cyber attack. So they have a minute left. What I would like to also show you, and I'll recap. Let me see if I have a recap slide. Recap here. So we have the past. The past is the AV era, signature-based and heuristics. The present is machine learning, the era, where we have detection on human-selected features. It's limited, but now the future, deep learning, has a higher detection rate, it skips the human engineering capabilities, and now you're able to feed it raw data in a file and actually train on the algorithm to create a brain now presented on a computer. And that's the future with deep instinct and deep learning. Now, I promised you at the end, and I know we might be going a little bit over, join the revolution of cybersecurity and find your passion. And we have a team here at Deep Instinct. We're growing. We're about 150 employees, and we're looking for a lot of talent. So if you know anybody who's interested in Deep Instinct, just type in Deep Instinct and go to our career opportunities page, and I welcome you to join my team. If you have the passion for cyber, also a passion for emerging technologies, please feel free to reach out to me. Or if you want to have further conversation around deep learning and Deep Instinct and how this can apply to your corporate environment or your small business, please reach out to me as well. I shared with you my LinkedIn. So with that, I really thank everyone for your time. I know it's quite a lot of information, a lot of slides. I think it was about 40 slides, but we went through it quickly. I hope you have a great day. I hope everyone here has a great day and stay safe. I'll leave this picture up. If you want to take your picture, just take your phone, open up your camera app, and it will automatically point you to LinkedIn, to my LinkedIn page.
Yep. So BN, I actually did that at the beginning, and you're right. It took me exactly to your LinkedIn page to connect. So also, you had mentioned about sharing your presentation with the group.
Yeah.
So I did touch base with Michael as you were going through the presentation, and he said that you got an email kind of from the speaker to send the bio and different things. There was some communication there. He said, if you just send it to there, we'll make sure we can share it.
Very good. I'll do
Okay.
that. I'll make sure I send it to Michael.
Okay, and then Jeff did say thanks, that he was just curious on the message response. Was there any other questions or anything from this session? Comments, anything you guys want to post in the chat?
Yeah, good stuff. Oh, awesome, good stuff. I like it. You know, that makes me happy that it's
All right.
relevant and it's fun.